Way down, thousands of feet below us, there are these incredible pressures just fighting to escape to the surface. So, what's holding them back? Well, it's a very carefully engineered fluid. Today, we're going to step into the lab to really understand the science of controlling drilling mud density, and we'll see exactly how this crucial balancing act is perfected.
So here's our game plan. First, we're going to dig into why this density is such a critical balancing act. Then, we'll get hands-on and walk through 3 key lab procedures: prepping a sample, making it heavier, and then, you guessed it, making it lighter. And to wrap it all up, we'll connect how these super precise steps in the lab prevent total disaster out in the field.
All right, so before we get into the how, we have got to understand the why. This whole thing is about a really high-stakes game of push and pull happening deep, deep inside the Earth.
It's a pretty important question, right? And the answer isn't some simple metal cap or a giant plug. Nope. The #1 line of defense against a catastrophe is the massive column of fluid sitting right on top of that pressure zone. The weight of that fluid has to be engineered to absolute perfection.
And this is the absolute core concept right here. Mud density, or what a lot of folks call mud weight, is basically a hydrostatic force pushing down. It has to be just strong enough to perfectly counteract the formation pressure that's pushing up. It's a constant battle of pressures, and the mud has to win.
You see, when that balance is just right, you're not only preventing what's called a kick, which is an uncontrolled flow of oil or gas, you're also drilling a lot more efficiently. Plus, you're avoiding super costly problems, like getting your drill pipe completely stuck down there. So, at the end of the day, getting the density right is everything for both safety and success.
Okay, let's head into the lab and see how this is all built from the ground up. Before you can even think about testing how to change mud density, you have to create a standardized mud sample. This is the foundation for absolutely everything that comes next.
Now here's something you need to know. There's no such thing as one-size-fits-all drilling mud, not even close. Just look at these different recipes. The base liquid can be totally different. Depending on the geology, engineers might start with something as simple as distilled water, or maybe brine, or even diesel fuel. Each one is designed to mimic a very specific environment thousands of feet down.
So, no matter which recipe you're using, the preparation is meticulous. First, you have to precisely weigh your powder, something like bentonite, on an electronic balance. Then, you measure your liquids in a flask. And here's a key part. With the mixer already running, you pour the liquid in and then slowly add the powder. You can't just dump it all in at once. Then, you let it mix for at least 10 minutes to make sure every last bit is uniform.
Okay, you've mixed up your base mud, but now you realize you need to make it heavier to handle a higher pressure formation. This is where a really important additive comes into play.
Everybody, meet Barite. This stuff is a dense mineral powder, and it's been the industry standard for making mud heavier for nearly a century now. Its magic is that it's heavy, but it's also chemically inert, so its whole job is to make the fluid heavier without turning it into a thick, gloopy sludge that you can't pump. It's the #1 tool for weighting up the mud.
And this isn't some kind of guesswork. This fantastic little formula lets an engineer calculate the exact amount of barite they need. You just plug in your starting mud density, the final density you're trying to hit, and the density of the barite itself, and boom, it tells you exactly how many grams to add. Pure science.
So the lab procedure itself is really straightforward. You start by measuring your initial density. Then you use that formula to figure out exactly how much barite you need. You add that precise amount to your sample, you give it a good, vigorous stir for about 2 minutes, and then you measure again. You should now have a heavier, denser fluid that's ready to control more pressure.
But what if you go too far? Or what if you drill into a rock formation with less pressure and now your mud is actually too heavy? Well, you need a way to lighten it back up, and that process is called the water back.
The idea here is really simple. It's just dilution. By adding a less dense fluid, in this case, just plain water, you can precisely lower the overall density of the whole system. It's the literal opposite of adding barite.
And hey, just like with barite, there's absolutely no guessing involved. This formula lets you calculate the exact volume of water you need to add to your current mud to hit your new lower density target. It's all about precision, precision, precision.
The lab process pretty much mirrors the last one. You take that heavy mud sample you just made, you use the formula to figure out the exact amount of water you need to add, you pour it in, stir it for 2 minutes to make sure it's totally mixed, and then you take your final measurements. And just like that, you successfully brought the mud density back down.
So, okay, we've seen how to prep mud, make it heavier, and make it lighter, all in a nice, controlled lab. But why is this constant back and forth so incredibly vital out in the real world?
Well, it's because the Earth isn't one solid, uniform block. As a drill bit goes deeper and deeper, it passes through all these different layers of rock, and each one has its own unique pressure. That means the mud's properties have to be adjusted constantly, in real time, to match these changing conditions.
And the consequences of getting this wrong, they're severe. If your mud is too light, you can't hold back the formation pressure. That could lead to a kick or, in the worst-case scenario, a full-on blowout. But if your mud is too heavy, you can actually fracture the rock itself, lose all your expensive drilling fluid into the formation, and risk getting the pipe stuck solid. It is a very, very narrow window for success.
So you see, these seemingly simple lab procedures, all the measuring, mixing, and calculating, they're the very foundation of what we call well control. This is the science that allows drillers to manage the immense and invisible forces of the Earth, making sure that operations are both safe and efficient. The next time you think about where our energy comes from, just remember the unseen science of mud, keeping everything perfectly in balance.